Last time we looked at Jacobi method by splitting up the A matrix that you're solving into L plus D plus U components. And today we're going to repeat the same process with the Gauss-Seidel method and derive the associated B matrix. All of these things are stepping stones onto doing a full analysis of the convergence of these methods. Okay, so last time we looked at the Jacobi method for solving the classic inversion problem AX equals B. And remember, Jacobi can be written in this form. Xn plus 1 equals x. Equals C minus B of x of n. And then we started on the route of how to analyze the convergence properties of these methods. That's really the key. So that's a vector there. That's a really key thing about a lot of this level 2 stuff is if we revisit a method, we're looking at how we can analyze the convergence methods. Here this is probably a new method, but we also need to analyze the convergence, and that's really where the mathematics comes in. Otherwise it's just sort of stating the method and running it. And we did this decomposition of our A matrix into 3 matrices, L plus D plus U. So D is diagonal, L is strictly, i.e. strictly means no diagonal, lower triangular, U is strictly upper triangular. And then with a derivation we showed that then you can express this B matrix in terms of this decomposition as D minus LU. Okay, and we'll come back to this result later when analysing the convergence. But all we have to remember is that there's an automatic process for determining this B matrix, and it will turn out that convergence properties of Jacobi will be all about this B matrix. But it's very helpful to do this decomposition. Notice this is similar but not exactly the same as our U decomposition, in the sense that these L and U matrices don't have diagonals. The diagonal goes into the D matrix, and this is the matrix we get. So what we want to do now is do the equivalent for Gauss-Seidel. Remember, we're looking at Jacobi and Gauss-Seidel as a pair, where Gauss-Seidel is faster than Jacobi, and we want to compare the two. And in doing so, we understand how iterative matrix methods work in general. So now consider Gauss-Seidel. Now, although you don't, with the Jacobi involves multiplying through by this B matrix repeatedly. Gauss-Seidel is not done that way. If you remember, it's about writing out all the components and doing a line by line calculation. So, but it turns out that it's helpful to put Gauss-Seidel in a similar algebraic layout to Jacobi. So for analysis purposes only, we are going to put, you call Gauss-Seidel GS, put GS in the same form as Jacobi, i.e. xn plus 1 equals c minus b of x of n, that sort of thing. Okay, so although we don't use it for actually the sort of computation of a Gauss-Seidel, it's helpful to put it in this form. That's what we're going to do first thing today. So first thing is we start from a line of the Jacobi derivation last time. So basically, if you go back to Jacobi, if you go to the lecture notes, page 46 in this case, so lecture notes, page 46, bottom, we have this statement here, xn plus 1 equals d inverse times b minus d inverse L plus u x of n. So this is Jacobi at the moment. This is, we haven't got the Gauss-Seidel yet. That's what we did last time, okay? So this matrix turned out to be C, and this matrix here turned out to be B, C minus B of x of n. Okay, and you remember the way we derived Gauss-Seidel before is we wrote out all the components and then we modified some of the entries from n to m plus 1. So before, let me try and give you a reference in your lecture notes. Okay. Page 46, top, we changed some terms from n to m plus 1. Okay, so that's top of page 46, and what we want to do now is that we did that sort of in a line by line sense. We want to see, well, we've got now it written down as a sort of matrix equation, is where, how do we modify this equation to do the same thing. Now remember, we modified terms from n to n plus 1 basically when they were available from the previous line. This will correspond to modify the L term above. Okay, so I'll make that a bit clearer in a minute, but let's just show it on this board. This lower triangular bit pre-multiplies x to the n, and it's those terms that correspond to change from n to n plus 1 when going to Gauss-Seidel. Right, let's write that out again. Just sort of an overview statement of where we're going. So Jacobi is xn plus 1, and basically going to expand that previous expression, just expand that brackets. So you have d minus 1 b minus d minus 1 u of x of n minus d minus 1 l Okay, so that's just expand. I've just separated off the L and the U terms separately. Okay. So that the reason I've done that now is that we can then see that then going to Gauss-Seidel, we're just simply going to modify this term, right? Because it's lower triangular. So let me just show you. So L has the structure. I don't have to show you exactly what the elements are, but the elements of the stars. Okay. And these correspond to values that have been updated from previous line in Gauss-Seidel. So, I mean, if you want to go through the example we had before, the first modification involved the x element, right? Okay, so that corresponds to that element here. You see L multiplied through that, right? So with Jacobi, that would be an xn term, but with Gauss-Seidel, that's going to be an xn plus 1 term. The next line down, we modified the xn and yn terms, so that's that element there and that element there. So you can see now that now separating off into this is why this L plus U plus D decomposition is useful. Helps us separate off Jacobi and Gauss-Seidel. We're going to modify that. Okay, so it's the L term. So maybe it takes a little bit of thought offline to figure out how that works. I'm just going to give myself some room again. Actually, let's use a rubber. I don't use that much. Oh. Let's just go to a new board. So let's just rewrite Jacobi again. This is Jacobi, and then Gauss-Seidel involves the modification of those terms. So we just write it out again, everything the same. Apart from this last term, which now is going to xn plus 1. Okay, that's a key change, n10 plus 1 there for the lower triangular term. So if we rearrange now of course, now we have n plus 1 terms on both sides. So now we want to get it Gauss-Seidel into a form that's like xn plus 1 is c minus b of xn. So we need to rearrange, get xn plus 1 on the left hand side. That simply means transferring that term and also we also going to multiply through by we're going to multiply by d as well. So we multiply through by d. So that will then give us L plus d, because d times the inverse is obviously identity. B minus u of x of n. Yep, so we've multiplied through by d, so that gets rid of d, that d inverse there, d inverse there, and d inverse there, and the d then goes in front of the xn plus 1. We bring the L xn plus 1 onto the left, so you've got L plus d times xn plus 1 on the left hand side, and then you've got b minus u of xn on the right hand side. So now all we do, remember this is a matrix problem, so we have to multiply by inverses, we don't divide through by matrices. So we basically multiply through by L plus d inverse now. Yeah. And that gives you, so that's just doing words, multiply by L plus d inverse, so all that inverse. That means that you get xn plus 1 on its own on the left hand side. L plus d inverse times b minus L plus d inverse u x of n. Let's write that at the top of this board again. So this is Gauss-Seidel now. We've modified the, xn plus 1 d plus L inverse minus d plus L inverse u x of n. So what we've done here with Gauss-Seidel, this is Gauss-Seidel, is we now got it in a form, although we would never compute it in this way, for analysis purposes very useful. We've got a C matrix here, so it's C minus B of x of n. So that implies C for Gauss-Seidel, C equals D plus L inverse 1b. We don't tend to worry too much about this C vector, it tends to get cancelled out a lot of calculations, but the most important matrix is this B matrix in terms of these matrices. So this is quite a long derivation, this is the longest derivation we've had, so there's lots of results we're getting that won't really be crystallized until when we use them for convergence analysis, but believe me, bear with me, there's real good reasons for doing all this infrastructure, if you like, because by the time we get to proving convergence of Jacobi and convergence of Gauss-Seidel, we've got everything in place. So it's sort of a case of sort of bearing with me for a number of videos, and then we see where we are. But it turns out that these B matrices are going to be key for convergence, and the B matrix for Gauss-Seidel. So the B matrices are key for analyzing convergence, and this is and given the number of practical problems that involve matrix inversion and big matrices, this is such a key sort of bit of analysis, convergence. So let's have a little look at the time. What I'm going to do is just have a quick summary slide of what we've got so far. We've got Jacobi and we've got Gauss-Seidel. And we've got this key result. So we want to get everything in the form of x n c minus b of x of n. That's what we're looking for. And for Jacobi, we found that b is d minus 1 L plus u. Whereas Gauss-Seidel is d plus L, or inversely, times u. Okay. So they all involve d and L and u, and these are the matrices here. And so this will enable us, because we've decomposed our matrices into d's and L's and u, it enables us to look at a matrix, break it up, do some calculations, and figure out whether it's going to converge or not, how fast it's going to converge. And that's an incredibly powerful result, because these matrix methods are the engines of data science, in fact, and also all computation. So it's really important to get, you know, this. And as I said, we're using the sort of oldest methods around, Jacobi and Gauss-Seidel, so we can really, because they're quite simple, to understand these methods. Okay, I'm going to stop now and see you next time.